There's another question, okay? And does that force, is it everywhere? You know, not just in our solar system, is it out in the universe? Okay, now we've already touched upon some of those topics in the last session, but we're going to go a little deeper. So here he is. This is a scene from The Principal. See the apple fall? You didn't catch that? Nobody catches that. Yeah. The apple falls and it's got Newton thinking, what made the apple fall? All right, so here, let's try to summarize Newton's little world. What makes up his little world? We already talked about this in the last topic, and the first thing we need to know is that Newton believed in what we call absolute space. Now, it's actually absolute space and time, but we're just going to focus on the space part of it. Absolute space, what does that mean? That means it can't move. It can't move. It's absolute. And the second thing is that his system, as far as saying why the Earth goes around the sun, is because he confined it to the solar system. Okay? Very important point. Everything else out there is absolute. But in our solar system, we have things moving. Okay? Even the sun is moving in Newton's system because the Earth and the sun actually go around a joint center of mass, which means the sun has to move just a little bit to go around that center of mass. But basically, the Earth is moving around the sun, and that's what causes 365 days, all our seasons, blah, blah, blah. There you go, okay? Now, anybody have any questions about that? Everybody have a good idea of what absolute space is, okay? Now let's go to another guy, Einstein, which came about 300 years later. In Einstein's system, it's non-absolute space. Non-absolute. And what does that mean? Well, if Newton's absolute space can't move, that means Einstein's can move. It can curve, it can bend, it can do gymnastics, it can do all kinds of things. Okay? So that's the first thing. The second is it includes the whole universe, not just our solar system. Now Einstein does have a version where he just deals with the solar system, just the sun and the earth. But he's required by his own relativity to have another system which includes the rest of the universe. Okay? That's just the nature of relativity. And he understood that. Okay? All right, but everybody got the two basic differences between Newton and Einstein. So Newton's preferred system was the heliocentric. And this is what he says in his scholium of 1684, 3 years before he published his Principia Mathematica. He says, "Thence, indeed, the Copernican system is proved a priori. For if a common center of gravity is computed for any position of the planets, it either lies in the body of the sun or will always be very near it." So he thinks he's proved heliocentrism. Okay, and the next, I just want to show you a little, so there you have it. There's the Earth going around the sun. You see the X in the sun? That's the center of mass. And so even the sun has to go around the center of mass, and the Earth, of course, does as well. So you would, in the Newtonian system, you would say the sun and the Earth go around a mutual center of mass. Okay? Now you should probably have a better picture of the center. What is the center of mass? Okay, well, I can tell you what a center of mass is, because when I play tennis and I play a bad game and I throw my racket, and I don't do that all the time, but if I did throw my racket and I threw it sideways, how is that racket going to turn around? Anybody ever notice that? How that racket turns around? Does it turn around in a perfect circle? No, it wobbles. Wobbles if I throw that racket. Why? Because the mass of the tennis racket is going around the center of mass of the tennis racket, not the geometric center, the mass center. Okay? So if that racket weighs 50 pounds, or 50 ounces on one side, and it weighs 30 ounces on the other side with the handle, the center of mass is going to be much nearer to the string side of the tennis racket than the handle side of the tennis racket. And that racket's going to go around that center, not the center of the geometric center where you get a 20-inch racket, and the geometric center is 10 inches. Okay, that's the geometric center, but that's not the center of mass. Okay, everybody understand that?
Also known as the barycenter.
Yeah, also known as the barycenter. Thank you. Now, for future reference, check this out.
All these illustrations come with your Galileo book on a little thumb drive.
That's right. They used to, actually. We sell that separately now. So what did we just see? We saw the Earth occupy the center of mass, and the sun and all the stars now going around that. Let's look at it again. Oops. All right, well, we'll skip that. Everybody understand that last video?
Was the center of mass still kind of wobbling?
Just a little bit. Yeah, I mean, probably not, okay? Yeah, and that gets into a whole other issue about the universe's wobble or precession, okay? But the universe and the Earth share a center of mass in the geocentric system. But the universe has a different axis, and that's why it's going to wobble, okay? All right, so now let's get into the heart of Newton's answer to the question that I raised before, which was, okay, you say the planet goes around the sun. What makes the planet go around the sun? All right, well, let's break down his system. So you see the sun. I'll turn on my trusty laser here. Here's the sun. Okay, and the reason this Earth moves is because of inertia. Somewhere, somehow, someday, someone pushed the Earth. And once you push it, it's going to remain moving. That's called inertia. Now, he doesn't tell you who pushed it, okay? We all know who pushed it, right? But he's not, well, we know who didn't push it. That's
right.
God, right? And so inertia makes the Earth keep on moving. All right, but in which direction is it going to move? Straight line. And what kind of space do you need to move in a straight line?
Euclidean.
Yes, Euclidean, but use the term that we used before. Absolute space. Okay, because if the space was moving, then you couldn't say that the Earth was moving in a straight line, because it's going to move with the space. And from the observer, it's going to look like it's moving in a curved direction. Okay? So that's why it's important for Newton to have absolute space. Otherwise, he couldn't say the Earth was moving in a straight line. Very important. All right, so that's the Earth's job, to move and move in a straight line. So if you want the Earth to go around the sun, what are you going to have? You're going to have gravity. that's going to pull it by this equation, mass times velocity squared over r squared, which is the radius. And they call that the centripetal force. So because the Earth is constantly being pulled by the sun, that means it can't go in a straight line. It's going to go in a curved line. There you see it, curved line around the sun. Everybody understand that? Okay? There's one other little tricky thing. See, when Newton's 3 laws of motions, any force is going to have an equal and opposite force. That's his 3rd law. And so you're going to have somehow, you have to have the effect at least of an opposite force to the centripetal, and they call that the centrifugal, away from the center. That's what centrifugal means. Centripetal means toward the center. Okay? But to them, this is not a real force. They just have to put it in their equations to make everything balance. That's an important fact. And so they just call it an effect, not a force. Okay? Everybody with me? If you don't understand it now, you may later.
I didn't quite get that. If you want to force versus effect, it's just a result of a response to the system.
Exactly. Yeah. So it's going to appear as if the Earth wants to go outward, but that's only because it wants first to go in a straight line, but this gravity is pulling it in a curved direction. So it's going to look like it wants to go outside, but it's not really the case. Okay? All right. All right, so here's the Newtonian system going around the sun. The Earth is rotating. Okay, and I have exactly the same descriptions here that I did in the last slide, except for one more, and that is the Coriolis force. And it's kind of hard to see the labels that I've put on here, but here you see inertia.
Tell us by color.
The white is inertia, the yellow is centrifugal force, the blue is centripetal force, hopefully it'll come up again.
And the other one was Coriolis.
Yeah, the pink I think was the Coriolis. Come on. Ah. All right, let's try this again. Oh.
We see it.
Yeah, but I tried to get it to play and it wouldn't play. Oh, there we go. Okay. Okay, so the only additional force I'm putting here is the Coriolis. And that also is an effect in Newton's system. It's not a force. Okay? Coriolis is an effect. And I'll explain more about that later. Let me just show you the basic components to the Newtonian system. Inertia, centrifugal effect, Coriolis effect, centripetal force toward the sun. Okay? Make sense? Good. This computer is slow.
Maybe someone can bring a faster computer for us to use
Yeah, that might be advisable.
later today or tomorrow.
Yeah. All right. So now we're going to analyze Newton from the eyes of Albert Einstein. And here's what Einstein says right here. Now, this is in the middle of a quote, okay, but you won't need to know the before stuff. You just need to know what I'm going to read here. He says, quote, whereby K, he always liked to use K for some reason. K, the Earth, is treated as being at rest. So in other words, Einstein's system is going to allow the Earth to be treated at rest. In other words, he's going to have two systems, one in which the Earth moves and one in which the Earth doesn't move. And he's going to show us in relativity that they are equal to each other. It's just another coordinate transformation, this time with forces instead of geometry. Okay? So continuing on, he says, if Newtonian mechanics disallows such a view, then this could very well be the foundation for the defects of that theory. Okay? In other words, what he's saying is, if Newton doesn't allow the Earth to be at rest and the universe to revolve around it, well, that's a defect in his theory, you see. Because his theory, as it stands, can't do it. He had to think, well, maybe if there's another force out there, we could do it, but he doesn't know what that force is. You know, he said that in that last page and never made it to his Principia. He said if there was another force, maybe we could get the Earth to be in the center, but he has no idea what that force is. You're just saying if there was a force, that's what we could do. So Newton's saying, or Einstein is saying, well, that's a defect in your system. If you can't reverse the two, can't reverse roles. And that's why relativity superseded classical mechanics of Newton. Okay, because Newton wasn't able to do what Einstein said he should to be a viable scientific thesis. Everybody knows him, don't we? Well, here's a gentleman who's had a long tour from being an avid heliocentrist evolutionist to at least acknowledging the geocentric system and perhaps creationism. He went to Parma, Italy. Well, first let me give you his background. He, in 1962, was at Vatican II. And I'm going to show you later that in his farewell speech of 2013, he talked about his presence at Vatican II and how excited they all were to go to Vatican II because they had some new things they wanted to bring to the world. And one of those things was that they were finally going to address the Galileo issue after 300 years and make everybody happy by conceding that the church was wrong. That's what he says in his quote. You can go look it up yourself. Okay? 2013. Almost 30 years later, he is learning a few things about cosmology, and he comes to the position that I'm bringing you to, that relativity has now superseded classical mechanics of Newton, wherein we can say the Earth could be at rest and the sun can go around it, or the sun can be at rest and the Earth can go around it. Either one could be correct. He's come to that position. And he went to Parma, Italy, at a university there to tell them about this. And this is what he says. Today, things have changed. Among these, an important role is placed by the affirmation of the existence of an absolute space. There you go. You see that? Absolute space. That's an opinion that, in any event, has been canceled by the theory of relativity. No more absolute space. Sorry, Newton. There is only a relative movement of bodies among themselves, and therefore the measurement of that depends to a great extent on the choice of a body to serve as a point of reference. What he means by that is, you got to choose somebody that's going to be the body at rest, that's not moving. And then the conclusion is, then as now, one can suppose the Earth to be fixed and the Sun as mobile. That's right from your Cardinal, Joseph Ratzinger, 1990. And you know what they did to him in Parma for saying that? They threw him out. They threw him out. Told him never to come back again. And he didn't, except like about 20 years later, he tried to come back and they refused to have him back. So, a lot of drama going on here, isn't there? Oh, yes. All right, so now back to Newton. So all this talk about absolute space and time, the universe being fixed and cannot move, being infinite, that's all going by the wayside, okay? Now we have a non-absolute universe. Now it's non-fixed, always moving, and it's finite. So F equals ma and F equals mv squared over r, and the gravitational equation, F equals gmm over r squared. They may work in a solar system all by itself, but they ain't going to work in the real universe. Okay? That's the distinction. So we can cross all that out. Okay? It's not going to work. Even in their own system, it's not going to work, and I'll show you why. So Newton is a dead end. Newton's force laws, F equals ma, that's force equals mass times acceleration. Now, you would think you could use that equation to show how the Earth would go around the sun. Okay? Let's look at it. Let's take it apart. What's the F? The F is the gravity of the sun. What's the M? The M is the mass of the Earth. What's the A? That's the acceleration the Earth has to have to go around the sun to stop from being pulled in by the sun. Okay? Now that seems to fit. Okay? Now, if you want to know what the gravitational force is between the Earth and the sun, well, you use the second formula below, and that's the F, that's the force between the two bodies, equals G, and G is a factor that they figure out to show what the strength of the gravity is. And it's a very small number, but it's always there nevertheless. G, the big mass, is the M, that's the sun, times the little mass, the Earth, divided by the distance between them squared. That's how you find the force of gravity between the Earth and the sun. Seems to work. Okay, yes?
And Hildegard of Bingen teaches us something entirely different about what gravity is.
She does, yeah. Now, but she will still have to go by these in a local system, okay, even though she has a different reason for why gravity exists in the first place. As a matter of fact, Einstein didn't have a reason for gravity. He didn't know what caused it. He just said, I can tell you how fast it moves. I can't tell you what it is or why that apple fell on my head or fell on my head. Okay? Now, he had some theories, but they were never taken as fact. Okay? And that's going to be an important question, is this whole gravity issue. Because if you can't tell us how gravity works, then what are you assuming when you say that the sun is pulling on the Earth? You're assuming that that gravity acts instantaneously. Okay? It doesn't take weeks to travel to the Earth, because if it did, the Earth would go off into space. You're assuming it travels instantaneously, and that's part of your theory, but there's no t value in your equations. There's no t value for time in your equations. So you're assuming that it's instantaneous. Well, how can you do that? You can't even tell us how gravity works. How can you tell us that it reacts instantaneously? Now, this is significant because when Einstein came along, he said gravity can only go the same as the speed of light, 186,000 miles per second, or 300,000 kilometers per second. Okay? That's the speed limit of gravity for Einstein. Well, Newton, he didn't have a speed limit for gravity. He said it acted instantaneously. All right, so here's another flaw that we found in Newton. Okay, so remember we talked about these three forces: centrifugal, Coriolis, and Euler. That guy's, it's not Euler, it's Euler, just for your information, Euler. Okay, like the Houston Oilers. All right, so these are three effects that show up in any movement that is not in a straight line. Okay, like when you're on a merry-go-round, carousel, you're going to feel these three effects if you look at it from the Newtonian system. Okay, so the carousel starts going around. When the carousel first starts, you feel what? Not that, yeah, you feel, tell me what you feel when that, you feel a jerk, that's right. That's the Euler force, okay? And now when the carousel is going around, you feel what? So you feel what? Tell me what you feel. Feel like you're going to be thrown out. So away from the center, and that's what we call centrifugal. Now the English say centrifugal, by the way, just to let you know. But that's what you're going to feel. Now what about the Coriolis force? Okay, let's say that somebody in the center of the carousel has a basketball, and you are on the rim of the carousel, and the carousel is going around. And he tries to throw that basketball to you. What's going to happen? Yeah, it's going to go to the right. Okay, if the carousel is going to the left, the ball is going to go to the right. That's the Coriolis force. Okay? But these are not real forces in Newtonian mechanics. These are effects. In other words, in Newton's system, there's not a force that's moving that basketball to the right. That just happens to be the geometry of the movement of the carousel against the ball that's trying to go straight. You see? It's just a matter of geometry. There's no force moving that ball to the right. The only force was when you pushed it out.
Like if you were in the wind and you're moving and I throw the ball at you, you're going to be over here by the time the ball's over here.
Yeah, but it actually is going to curve. It is going to curve. Okay, so that's the tricky part about that. It's not going to go in a straight line. Okay, so just as long as you understand the concept here. Okay, let me move on. Oh, another way, he called these, instead of calling them forces, he called them fictitious forces. They're not real, they're just effects of motion, is what he's trying to say. All right? Okay, so let's delve more deeply into this issue. Hidden fact of modern science. NASA and the JPL, that's the Jet Propulsion Laboratory, cannot get a space probe to go where they want it to go using Newton's laws of motion. You heard it here first, folks. Okay? In other words, they can't just use F equals ma. What do they have to do? They must add into the equations the three inertial forces: centrifugal, Coriolis, and Euler, which are not part of Newton's system. Why? Well, because it's only F equals ma. You don't see centrifugal force there anywhere, do you? Okay, so when you get down to it, come up here for a minute. Bring that up. Watch that last leg. It's crumbling. Is that stable?
Let me take this off first.
Okay. Excuse us while we adjust. Spread them out. Spread them out. There you go. Okay, and put that back up there. And get me that black pen. Yep. Okay. So here is Newton's formula. F equals ma. If you tried to use that to get a space probe to go to Mars, it would never get there. What does he have to do? He has to add in the centrifugal force plus the Coriolis force plus the Euler force. That will get the space probe to Mars or Jupiter or wherever they want to send it. Okay? Without that, it ain't going to get there. Now, these three things are not part of his system. He has to add them in by hand. By hand. In other words, he's got a foreign element out here that he's going to put into his equations to make them work. Now, let's go to Wikipedia. Wikipedia has a little section on Coriolis force. You can look this up yourself. Now, let me warn you, whenever we find information on Wikipedia to support geocentrism, that sentence will invariably come off. You may find it in the talk section, but it'll come off or be reworded so that it's the same, but it's not really the same, okay? And I've seen this many times, all right? So I document anything I download from Wikipedia these days. But, and this time in April 14th, 2019, when I downloaded this, it says, quote, as a result of this analysis of what? Of how to shoot a cannonball, launch a satellite, get a space probe to go to Mars, whatever you're talking about, all the fictitious accelerations must be included to obtain the correct trajectory. Got that? All the fictitious accelerations, these are all accelerations, must all be added to obtain the correct trajectory. And what is a trajectory? That's the path that satellite's going to take, or that probe's going to take to get to Mars. Okay? Everybody with me?
Yes.
Okay. So the Newtonian system, let's ask this question. From where does Newton borrow the three inertial forces to make his system work? From geocentrism. Because in geocentrism, these forces are actual forces. They're not effects. They are part of what you get when you have a universe that's rotating. You're automatically going to get centrifugal, Coriolis, and Euler forces. We don't have to add them to our system because they're already there. But in order for Newton's system to work, he has to take it from us and put it in his equations. And for 300 years, they've been doing this to us without telling us the real origin. But of course, they didn't know it until Einstein came along. So we'll give them a break. So here you have it. The Newtonian system is F equals ma plus fudge factors. The geocentric system is F equals ma plus the three inertial forces. So now we're going to ask, how does the geocentric system work? Excuse me. Yeah. Question?
So are you saying that every launch of a satellite or, like artillery is using a geocentric system to predict or to guide them?
No, I wouldn't go that far. I would say that they are stealing the geocentric forces and putting them into their Newtonian system to make it work. That's as far as I would go, okay? All right, did everybody see that? There's this phenomena that occurs in the sky when we look at Mars. And Mars will be going like this, and all of a sudden it will turn around and come back for a few weeks, and then it'll stop and come around again and go forward. That's called retrograde motion. As a matter of fact, all the planets have retrograde motion. Mars has the most distinctive, and it's the closest to Earth. And for years, the heliocentrists have been trying to use that as proof that the Earth moves around the sun because of that last. No, I don't know if I'm going to get it to play again. Okay, now this is how the geocentrists explain it. You see Mars up here at the top. Now it's going back, and then it's going to go forward again. And you see, it's caused by the sun that's carrying Mars around a fixed Earth. So you can't use that as proof of heliocentrism, of course, if you can show the same thing in the geocentric. Yeah, let me try to get the heliocentric one up here. Here you go. See, there's Mars. Now it's going back, and you see Earth and Mars down here at the lower part, Earth going around the sun. So that's the heliocentric.
Tell us, what sphere is this?
Yeah, well, there it goes. So I should have made it longer.
That squiggly line is just representing what's the smaller dot.
All right,
Earth is blue.
yeah,
Mars
Earth is
no-
blue.
What's this,
That's
this
Mars.
middle sphere?
That's Mars. Whoop. That's Mars and that's Mars.
So that's just,
Okay, so we're just extending Mars out here. Okay, here we want to show you that it is really close to the Earth in the orbits. Okay, but here we want to show you what we see out in the sky.
Okay.
Okay? So let's see if this one will play again. Now this all relates to the Newton stuff. I'm not just showing you just, for no reason here. Now we're going to look at the, this is the heliocentric one. We just saw the geocentric one. Okay? Now the sun is in the middle, and the Earth is going around the sun, and so is Mars. Okay? And then we extend Mars out here so you can see the retrograde motion that it makes. All right? So there you have it. Same motion that the geocentric can give when the Earth is in the center and the sun is going around it, as long as the sun carries Mars with it. Okay? Everybody see that? So I don't need to go over it again?
No,
Okay.
it's in your book.
Well, the video isn't in the book. That's the problem. The video is on the flash drive.
Sounds like some folks would like more explanation.
You would? I can't. All right, now, have you ever heard of parallax before? Parallax is the empirical means of judging the distance to the stars. Okay, so first I'm going to show you the heliocentric parallax. Now, here is the sun, here's the earth, and here are two stars, one farther away from the earth than the other. Okay? And so this is what you're going to see happen between these two stars. This star is going to move to the right, and this star is going to stay still. And then what you do is you measure the angle that this bottom star moved, and you use the Pythagorean theorem, and you can tell how far away that star is. Very easy. Okay, so for years, this has been used as proof of the heliocentric system. Okay? So let's watch it. Now watch these two stars. Watch the star move to the right. Because this is what you're going to see from Earth. And there actually is an angle. Look at that angle. Okay? Because the Earth started here, and it takes 6 months to get on the other side. And between those two times, you're going to create an angle between those two stars. Okay? Everybody see that?
Or heliocentric.
Now we're going to go to the geocentric one. This thing would move. Come on, baby. It just won't move for me. Let me see here. All right, so good. Here's the geocentric one. Watch this. You see the sun is now moving around the Earth in the same 6-month period. But what is it also doing? It's carrying the stars with it. Okay? Because they're all moving, because the universe is rotating. They're all moving together. So what are you going to see?
The same thing.
Same thing, same exact thing. Okay, here it is again. Well, started to. Okay, same exact thing. So that's why parallax is no longer a proof of the heliocentric system. Yes, sir.
So this is an example of, doesn't stellar parallax prove heliocentric? And you showed us, no. Your volume 1 of Galileo is wrong, the church is right, has about 40 such instances of so-called heliocentric proofs, and you point out it's not a heliocentric proof.
Yeah. Remember that man we quoted at the beginning? Lincoln Barnett, the historian, and his book was about Albert Einstein, and Albert Einstein wrote the foreword to it, and he says, there has been no experiment that has ever proved the Earth moves. Okay, why? Because he knows this, you see? Yeah.
I have a question. So if you're Earth here and you have all the stars moving around it, how fast are those stars actually moving in order to revolve around the Earth?
They're moving pretty fast.
So do they have a speed of light limitation?
No, they don't. And we're going to get to that. That's one of the most important questions. Okay? Where did this limit to the speed of light and material objects come from? And you're going to be shocked at where it came from. Yeah, I think that comes tomorrow. So we got about, what?
10 minutes.
You got 10 minutes?
We have lunch at 1 o'clock.
Okay, so, all right, okay. All right, let me move on to see what else I got on this section.
Take longer if you want.
This thing is just not responding.
I'm going to put in a request for anybody who
Okay.
has a laptop we can use the rest of the day or
All
tomorrow.
right, here is a simulation of a rotating universe. Check that out. You see the sun going around the Earth, the planets going around, connected to the sun. Angular momentum produces inertial forces. That is a fact of science, fact of physics. The inertial forces keep the stars and our sun in position. The universe rotates around its center of mass, the Earth. I think that's all I have for that. As the center of mass, the Earth cannot move. By definition, the center of mass does not move. Okay? within that system. Okay, so the other point I made here was that the inertial forces, and what are the inertial forces?
Euler, Coriolis, Centrifugal.
Right. All those forces, what do? They hold the stars, the galaxies, everything in its place. That's the gravity, if you want to call it, okay? They hold them in their place, and so as the universe rotates, you see the sun going across the sky the same way every day. You see, Orion going across the sky every day. Why? What's making it do that? The inertial forces that's created by this rotating universe. They permeate the universe. Okay? Now, I'm not the guy who made this up. I got this from Albert Einstein. Okay? And I just said, hey, this will work well for a geocentric universe. This explains the dynamics that we've been looking for all these years. Because before we've just been talking about geometry. But now we got forces that control the universe. Wow. That's pretty cool. Okay, so now what do we have? Check this out. So now you have the angular momentum of the universe controlling the movement of the sun by the inertial forces that are created by that rotating universe. So that keeps the sun 93 million miles away from the Earth, so that it can't go back, it can't go forward, it can only go where the universe allows it to go. Okay? And again, we'll see more of this later on. I'm just giving you a taste of it now. But that's what's going on. Okay? So the red arrow here. Oh, sorry. Let me see if we have anything else. Come on. Yeah, we're going to need a new computer. Oh, okay. Here we got a diagram of it. So Earth is fixed in the center. Okay. Here you have the sun. And it doesn't matter how big the sun is. Okay. Doesn't matter how far away it is. Okay. It's all going to be controlled by these inertial forces. Because as Einstein told us, they act just like gravity. Okay. And the Coriolis force, as a matter of fact, is going to make the sun curve around the Earth. Because the Coriolis is a curved force, a curved inward force. Okay? The centrifugal force that would tend to make the sun go out is neutralized by the Coriolis force, because the Coriolis force, as we will find, has twice the magnitude of the centrifugal force. Okay? Twice the magnitude. And that ends up making the sun curve around the Earth.
So is the centripetal force not really a force in this system?
Not really. Compared to the mass of the sun, it's negligible. Yeah. So it's basically the inertial forces that are taken over, you say. All right? Let's see what else we got here before lunch. All right. So remember I just said that the Coriolis force has twice the magnitude of the centrifugal force? Well, here is the common equation that they use all over the world when they want to compute, let's say, wind speeds, like when the National Weather Service wants to figure out what the wind speed is. Well, they use this formula. Why? Well, because the Earth, in their understanding, is rotating, and that makes it a non-inertial system. If the Earth was fixed, that would be an inertial system. And whenever you switch from an inertial system to a non-inertial system, or from a non-inertial system to an inertial system, you have to use this equation. Okay, and what does this equation have? It has the three inertial forces. Okay? So we're just using what everyday meteorologists use or physicists use. Everybody has to use this equation. Even Newton, as we found, to make his probes go to Mars or Venus or wherever he wants them to go. You have to add these in there. But for our vantage point now, as to answer why the sun goes around the earth, that's because the Coriolis force is twice the magnitude. That's why you have the 2 before the omega, as opposed to the omega of the centrifugal force. Okay? Now let's go to Wikipedia again. It says, in this case, the Coriolis force is twice the magnitude of the centrifugal force, and it points in the centripetal direction. What's the centripetal direction?
Towards the center.
Towards the center where the Earth is. The vector sum of the centrifugal force and the Coriolis force is the total fictitious force, which in this case, I forget what that says. All right, but we have enough information here. I just have to make this slide a little smaller. You notice how they call it fictitious force? Yeah, because they're not going to admit to you that they need these forces to make their system work, so they'll just call it fictitious. And who knows better, huh?
Like Newton did.
Like Newton did, exactly, okay? But in the geocentric system, they are real. They actually exist because the universe's rotation creates them, okay? But I just wanted to verify for you that the Coriolis is twice the magnitude. That's our key equation there. All right, who can we thank for this knowledge about a rotating universe? Albert Einstein. He says, we need not necessarily trace the existence of these centrifugal forces back to an absolute movement of K prime, the Earth. Okay? In other words, the conventional Newtonian system says because the Earth is rotating, well, it creates its own centrifugal effect, and that's why we have a bulge to the Earth. And the ratio is 231 to 230. So, but he says we see this centrifugal effect, even though it's not a force. It's happening because the Earth is rotating. That's the Newtonian system. So Einstein comes along and says, well, we don't have to attribute the centrifugal force to a rotating Earth. We can instead just as well trace them back to the rotational movement of the distant ponderable masses, the stars, in relation to K prime, the Earth, whereby we treat K prime Earth as at rest. Got it?
Yep.
Earth is at rest. That means the stars are moving. And they're going to cause the same bulge of the Earth as if the Earth were rotating under a fixed star system. That's what relativity gives us. Okay? Oh. Who can we thank about the Coriolis force from created by a rotating universe? Yep, same guy. He says in his letter to Ernst Mach, 1913, part of his general relativity theory, he says, if one accelerates a heavy shell of matter S, then a mass enclosed by that shell experiences an accelerative force. If one rotates the shell relative to the fixed stars about an axis going through its center, a Coriolis force arises in the interior of the shell. That is, the plane of the Foucault pendulum is dragged around. In other words, what he's saying is, you know that Foucault pendulum you see at the Franklin Institute? At least I have when I lived in Philadelphia. And it goes back and forth and it knocks down the pegs. Well, they always said that that's because the Earth is rotating. And now Einstein is saying, well, not necessarily. You could have the Earth fixed and have the stars go around that fixed Earth, and it's going to make that Foucault pendulum keep changing its plane every time it goes back and forth. Same thing's going to happen. Okay? Who can we thank for letting us know that the inertial forces act just like gravity? Yep, same guy. Quote, the centrifugal force that works on a body under given conditions is determined by precisely the same natural constants as the action of a gravitational field on the same body, in such a way that we have no means to differentiate a centrifugal field from a gravitational field. This quite substantiates the view that we may regard the rotating system, K prime Earth, as at rest, and the centrifugal field as a gravitational field. Wow. I couldn't have said it better myself. Everything I've just said to you is wrapped up in that one paragraph. Okay? All right, topic 4, next time. Time for lunch.
Would you take questions from the audience on the stream?
Audience on the stream? How am I going to hear them?
Well, they're typing it to me.
Oh, they're typing it to you.
Someone from
Okay.
the Netherlands.
Grace and blessing.
Okay.
Holy Ghost. Amen. Bless us, O Lord. Please like this.
You're about to receive, and I bow to you through Christ our Lord. Amen.
Amen.
Yeah.